So, welcome everyone. My name is Dennis. I work at Imandra, and today I wanted to kick off a series, maybe two or three in total, um, talks about how we've effectively adapted um, approaches for formal modeling of real kind of very large industrial software systems for the age of LLM agents. And so this is kind of the part one. There's going to be part two and most likely part three. But I wanted to use this talk as an opportunity to set up the kind of the problem statement and provide a let's call it a hello world or a very basic example manual of how one would go and start to model complex software system in IML. So this is all assuming that you guys have installed Imandra X, um, and you have the API key, and you have the VS Code extension, which we will be using right now. So, okay, let me just share my screen. Okay, so LLMs are incredible for coding, but when it comes to really thinking about large contexts, looking at very large software systems, it's very easy for them to miss certain edge cases. And that is very problematic when you're dealing with kind of real world systems. Moreover, you have typically different types of artifacts for any software component. So, what I mean by that is you might have a requirements document, you might have obviously the legacy source code, you might have log files, all of these basically things that have to be connected to and become part of the context, the reasoning context when these agents reason about code and also make modifications and so forth. So it's also difficult to just ask an agent to come up with a kind of arbitrary shape of how to formalize a large system. So what we have done over the years is primarily working in finance, but also in defense sector, is created a certain number of um, let's call it not templates, but let's say approaches to modeling really complex systems. And what we're going to be building out here today is this kind of approach of how we can take those experiences and um, again adapt them for LLMs. So the step one of the talk today will be all about us kind of manually creating this and going through the process. And then part two and three will be using something called SpecLogician, which is a kind of a framework for helping LLM coding agents to automatically use this approach to scale reasoning about really uh, complex systems. Okay, so all of this will be uploaded later to the SpecLogician examples, and we'll send this out later. But let me just kind of start going through the problem statement that we have. So I'm gonna just make this guy bigger. So let us just consider we have some legacy Python code. It's doing something stateful. Someone is logging in, they're logging out, and they're unlocking some resources. Okay, so we also have some requirements, and you have typically English prose that is supposed to define what this component does. Moreover, we also have some what are called traces, but they can be log files, that can be test cases. So, but effectively concrete traces that we will run through the system. So, our objective is to combine all three of these artifacts into a single model. And what typically happens in the real world is there are going to be discrepancies or inconsistencies or um, is underspecified, let's say, requirements, bugs in code, so forth. So what we want to do is we want to create a systematic process driven by LLMs that aggregates all of this information to a single mathematical, a logical model of the software component. So yeah, let's go through these things again. And our experience of effectively working with these types of artifacts is when you have requirements that can be over 1,000 pages long. Obviously, legacy code is just tremendous, and you have gigabytes upon gigabytes of log files, and the objective is to say, okay, uh, how do we aggregate all this information and understand, is the production system buggy? Are the requirements wrong? Is there some third party component that's used in the production system that leads to functionally bad outcomes? So all of these things really have to um, become coupled, and we're going to use Imandra X and IML to help us structure all of this information once. Okay, so before we proceed, I wanted to, and again, this is, you can go through this if you have Imandra X plugin and you have the Imandra Universe key setup. And if you go to codelogician.dev or imandra.ai, both of those pages have instructions for how you can set this up. But the overall, let's say, as part of this process, we're going to be creating is effectively a formal model of the system. And there's a certain specific way we're going to use them to create it that'll help us make sure we understand what is underspecified. We can easily link all of those artifacts, again, legacy source code, requirements, test cases, log files, etc., against these things. So kind of think of it as not only creating a mathematical model of the system, but also creating, in a sense, an accounting system, something that keeps track of all of these artifacts. And so the way that we're going to effectively produce this um, is by um, creating state definition. So this is just looking at kind of hello world example of this stuff. So the kind of core types in the Oracle domain model, it will have the state. So let's say in this case, it's just account, which is an integer, and action. And there's a lot of other kind of domain specific code that we can add to this. For example, if you're building a risk trading system in finance, this block will have a lot more kind of definitions about risk calculations, so forth. So all of those things that you can encode in IML. But the high level, the two kind of type definitions that we need to make all of this work is, number one is state. The second type is action. And then this should be saying block 2. So let's call it two. Let's just define it like that. So we also define what is the initial state. And then we will define two types of predicates on the state. So these guys just basically, you can see here, these are state only predicates. They just take in a state as the input variable and they return Boolean value. So this is just says, okay, is the count 0? Is this greater than 0? Is this exactly 10? Greater than or equal to 10? You can see these things. Then the other type of predicate is um, one that takes in the state and an incoming action. And what you see here is just basically, we're not using the state here at all, but you can extend this. And similarly, you can just also, this is fairly generic approach. You don't have to even use the action itself. So really, all of these things are functions that are structured this way. And the reason you can see we're kind of starting to um, define these predicates and with these types so forth is because typically for a large complex system, you're going to have thousands of these. So this structure you will see later will help us to make sure the accounting of these things is correct. And when LLM agent is creating this kind of incremental model of the system, it's going to do so in a way where the consistency is checked at every single permutation or change to the state of this model itself. Okay, so those are, we started out with defining what is the state, what is the action, what is the initial state, and then we have a bunch of functions that help us kind of define what is the current property of the state. And then where we start to build out the kind of the functional definition or functional description of the model is by introducing these what are called scenarios. And you can see here, we're just going to say, and this is very much, it is designed to be very similar to the way that people right now are doing what's called spec-driven development, and hence the name SpecLogician, and test-driven development, behavior-driven development, all of those things. You typically have collection of effectively predicates as part of the given. So um, this definition of the scenario is just saying counter 0, click occurs, then this typically refers to transition function. So which we have not gotten yet. So, but we have already looked into these predicates that will effectively be used for the given and when. So given here will be a collection of references to these state-only predicates. And when is going to be effectively the same. It's a list, and all of these predicates must be true for this scenario to be valid. When you have state in action. So basically, is click, is reset. These pertain to the when block. These guys can be used in the given block. So the given block can be empty, or it can be any collection of basically these guys. And as you noticed, if you start to define a scenario, like for example, is 0 and has been clicked together, they can never be true at the same time. That's when you'll start to get inconsistent scenarios. And as part of SpecLogician, which will be, again, it's kind of part 2 or 3 of the series, we're going to show you how SpecLogician automatically performs this analysis of consistency, not only within the scenario itself, again, when you specify things like given the counter is 0 and the counter is also not 0, but also when you have kind of intersections between scenarios. So when you're defining, let's say scenario 1 says the counter is 0, but scenario 2 says that the counter is not 1. So it'll identify overlaps. And our objective as we're creating this kind of formal model is to define scenarios so there's no overlap and all of the functionality, all of the state space is covered. So we'll go through that as well. Okay, so you can see here we're now starting to actually write out this. So these are all basically checks. So these guys right here, we have encoded them as this check on scenario 1 or scenario 0. A. And you can see here we're referencing 0 and is click, which is exactly what this guy was doing. Similarly, here we resets declare the counter. This is just description of the scenario. And since the given the scenario has been clicked, we just have this predicate and reset occurs. So is reset, we just check to make sure that the incoming action is in fact reset. So here is the kind of the third category of these functions that we define as part of this kind of the domain model is these are transition functions. And transition functions, unlike predicates, which return Boolean values, transition functions take in the state and action and return updated value of the state. So you can see here, we're basically just incrementing counter, and here we're resetting this. And so transitions will go into the then block. And evaluator right here is actually just kind of putting together all of those scenarios into one block. So it just says, okay, if scenario S0A checks, so all of the predicates are true, the ones that just deal with state and the ones that deal with state and action, which is this guy, then we're going to execute this transition S0A. which is this guy right here. And so, effectively, what we have done is we have, in somewhat, let's call it verbose way, encoded this logic about this counter. But again, you could have, written this in, I don't know, maybe 10 lines of code altogether, and it would have been done sometime around here. But once kind of the systems that we model become more and more complex, you'll see that kind of keeping this segregation not only allows the system to kind of incrementally build out something that just is really complicated, and complex, but also allows us to add accounting to these components. So, for example, it could be that somewhere in the requirements document, you say that, okay, we have to increase the counter when something occurs. And again, the requirements document could be thousands of pages of English prose. So what this will allow you to do is to actually map out, well, the LLM agent will be able to map out this to a specific text within the requirements document. But at the same time, you'll see this, the transition will also flag it out, what, you know, in which scenarios does this show up? How does this reconcile against the log data, the test cases, so forth? So it kind of creates this, again, this kind of a mathematical accounting system of all of these different artifacts and components. Okay, so and this evaluator you can see gives us an actual executable model. So we can say, okay, this is our initial state, this is an action, and we're going to produce a state. So right here we have effectively created a fully functional model of this thing. So if something else is we're kind of building out all of these things um, incrementally, what we will also want to do later is be able to actually understand, okay, we have these two scenarios. Is there something that is um, left out of this kind of definition? So we have these two kinds of checks. Is there some part of the state space that is not covered by these guys? And that is where this kind of Imandra region decomposition comes in handy, because it can symbolically describe to us, say, okay, you have these two scenarios. Number one is, both of them individually are consistent, and there's no overlap. And here is the effectively, here's the complement to them. So this is the functionality that will show that is not covered by both of these scenarios. Okay, so this is the kind of the high level idea of the approach that we're taking. So I don't know if okay, perfect. All right, let's start going through something a bit more complex. Okay, so let's go through kind of a more complex example. So we have this requirements document. So you can see here where effectively there's a login service. You can log in, log out. There's going to be, fail login attempt, all of these things. You can reset, so forth. So just a very basic model that has a requirements document. We have some legacy code implementation of this, which is kind of stateful. And we have a bunch of traces that we want to connect to all of this, basically all of these things. So the first thing we're going to do is, again, we're going to define, okay, here's what our state is going to look like. So, is the user logged in? It's Boolean. Is the user, how many times has the user attempted to log in? And then we're going to create this kind of simplified action type. So let me just go through kind of, to reiterate, we're going to be effectively creating the domain model is going to have types. And again, for really complex things, you're going to add a lot more stuff there, and really complex code that, again, could be doing risk calculations, some parsing, modifications, whatever really um, the system will need And then transition functions, predicates, and scenarios. So this is what we're going to build out again here. So in this state and action, so hopefully these things make sense right now. The second step for us to do is to start to build out these transitions. And you can see here, um, whether we have transitions first or predicates first, it doesn't really matter. Fundamentally, once we start to build out scenarios right here, we will want to um, uh, effectively use these transitions. But right now, we don't have to. We don't have to start with predicates themselves. Okay, so you can start to see here we're actually adding in details of where this logic came in from. So in the requirements document, we can see that, okay, if we can just take, let's say, snippets of the English prose and add them to this thing. Um, this is also um, some other parts of the system you'll see also reference the actual original source code, so forth. So again, in later videos, we'll show you how you can use SpecLogician to automatically build out these really complex relationships. Um, again, for really like very long requirements documents and trace and so forth. But here you're seeing that we're effectively writing out these transition functions with references to the actual um, requirements document right here. So this is not a greenfield. So we're assuming that we already have, let's say, this Python file like legacy.py, and we have some requirements documents, and then we have traces. So in fact, actually, this is not a greenfield project. This is an existing project. And what we want to do is we want to use an agent to go out and build a mathematical model. So in fact, it's actually the opposite of that. So we already have, let's call them, these are traces, could be log files or test cases or both. We have already legacy code and we have requirements document. So in fact, this is really um, the opposite of a greenfield project. We are creating a new model for this. Yes, absolutely. But we're doing that in a way where we can actually link up all of these different artifacts together with this thing. And so the idea is if you want to use a coding agent to effectively reason about, let's say, this legacy code, but you want to do it in a way where it understands what is the actual requirements. Maybe there's a mismatch between requirements and code. Maybe, and who knows which one is correct. And you also want to link it up to the existing, let's say, production data, so forth. This is what we're effectively building out here right now. You can use this obviously for new code as well. But what typically is like if you want to use AI to help reason about existing code or make changes to this code, what we're going to do is we're going to first create a mathematical model of this, and then you can make changes to it. You can make sure that the changes are correct, so forth. So, but this is exactly the target audience for this is people that already have code right now. So, and this is really, we're coming from kind of finance background. So if you go into any bank or any large financial institutions, there's, hundreds of really complex systems that, many of them have been written even things like COBOL, and the people that wrote them and understand um, how they operate are long gone because they retired, so forth. So this is really how do you go into these organizations and use AI in this way? Okay, but yeah, great question. Thank you. Thank you for it. Yeah, so this is again, we're creating new model of an existing legacy system. Okay, and you can see here, we'll start to build this out, and we're kind of again, this is a very manual thing we're doing right now. SpecLogician, which we'll cover in the next video next week, hopefully, um, will it's effectively it's a kind of a CLI utility that LLM agent, Claude, Codex, so forth, can use to kind of introduce these changes. And a lot of this kind of consistency checking and other analysis is performed automatically. And what's really powerful about it, again, is because once you go into really industrial, real kind of software, there's so many of these steps and transitions and data that you want to check. How SpecLogician does it is it just automatically checks this kind of consistency and performs this analysis using Imandra deterministically very quickly in a way that LLM agents would, not only would it not be able to match the logical rigor of Imandra X, but the speed at which it performs this is just so much greater than LM would ever do. And it also helps you because it doesn't make your token count go crazy. So, okay. So again, we're building out this kind of first transitions. Again, just what's the current state, what's the action, and you can see here, for example, we don't even care what the action is. So this is we're just updating the states here. Okay. So let's also look now. Let's start to add predicates. So there are two types of predicates. The first kind is what are called state predicates. This is just the value of the state, returns true or false. The second types are states and actions. Again, these correspond to the state predicates correspond to the given kind of clause in the scenarios. The state and action predicates correspond to the given, when, the second um, part of the scenario, the when. And here you can see we're defining these state and action predicates. And sorry, these are transitions. Right here is where we're defining the state predicates. You can see just logged in, so forth. And here you're seeing, okay, for example, login attempt, we don't even care that, what the current state is. It's just basically state action. So the reason why we're kind of keeping this signature like this is because, again, once you have thousands of these guys there, maintaining this kind of framework just makes it easy for the accounting to be quickly checked. Okay, so now let's go to the scenarios. So this is now we kind of defined, what is the state, the actions, what's the initial state, what are the different predicates and transitions. And so what we're now doing is we're defining again kind of scenarios using this, common methodology for given and when. So, so these checks basically for each of these kind of scenarios, they just invoke or they call these different types of predicates collectively. And then we have the different transition functions. These are, I think so we've already defined them. And then you can see here, this is kind of the evaluator. So this is call it the, historically, we also use this step function or just something that takes in the current states and the current action. And depending on which scenario it is, that invokes the transition function for it. So you can see this, if predicates from scenario 1 are true, then we'll call the scenario 1 transition function, so forth. And again, just looking into what SpecLogician does, the CLI utility and the kind of the framework for it is when your LLM goes through, let's say you give it PDFs, you give it source code, all of these things, and it kind of looks at different parts of the system and it starts to say, okay, well, in this scenario, this is what the outcome should be. And then it kind of writes it and adds the logic. What SpecLogician does under the hood is after the state is changed, after the LLM coding agent makes that change, what it will do is, for example, it'll go and make sure there are no overlaps between these different scenarios. So they're kind of mutually exclusive. And this is where this kind of power comes in, because you can just get the agent to go traverse all of your artifacts, source code, documentation, so forth, start to build out this kind of description of the functionality of the code that you have. But when it does that, you don't want to, you don't want the agent to go and start to introduce, inconsistent scenarios or things that are overlapping. And so, in SpecLogician, we'll show in the next video how we automatically um, we automatically check to make sure that these scenarios are in fact disjoint. Okay, so yes, and then another thing which is very important is when this kind of evaluator, which again tells us this whole, effectively the whole functional definition of our model, we also want to understand, okay, what actually is not covered by these checks. And I'll show you in a bit how we can do that. So one of the core features of Imandra is this ability to understand the state space. So you can see these guys, for complex systems, there can be virtually infinitely many possible state values and actions. And what we want to do is we want to say, okay, this logic is effectively disjoint, so there's no overlaps here. And there are no other values of the state that can basically fall through the cracks, are not covered by any of these four scenarios. So we'll go through that in a bit. But I want to go through it quickly and just kind of show you how we build this out later. But this is where kind of automated reasoning, logical reasoning comes in and feeds this information, feeds the coding agent um, to make sure that it understands what the gaps are. Okay, so what are we doing here? So um, effectively, let me just go through legacy. So we have this code, and what we've done is this kind of up until effectively these kind of scenarios, what they do is they all correspond to the some legacy code, etc. What we're doing now is we're actually just extending that model because there is information and requirements that just was not present. And you can see here we're kind of expanding on the functions, and we're also saying, okay, this is the source, this is where it came from, etc. So we're now extending these predicates and the transition functions that correspond to this new functionality. So, and we're going to go through and effectively just accumulate. So now we started with the one model, we define everything, and then we are effectively just um, adding more information, making sure it's all consistent. And I think actually, let me just very quickly restart. I had some internet outages right before the video, which is always helpful. So I just bounced the connection. So you can see here we're starting to um, write some verification properties about what can happen if you have some buggy logic, so forth. So this is also something that LLM agent can do. And here, when we go to this guy, hopefully, oh, this is so interesting. So this is actually, we failed to implement this correctly. This is, you can see, this is the power of formal verification. Even like for basic code, you think something is true and you fix it, and you get a counterexample from the stuff. So I'll need to go and kind of go through this in more detail and fix it. But this is a great example of making changes to code that you just kind of assume is true, and then you get a counterexample. So this is a Imandra's verify kind of command. You can see this is um, automatically um, kind of telling us what the counterexample to this verification goal is, etc. So this is going to be fun to go through this in a second. But let me quickly kind of go through the other components here, which is just as important. Okay, so we obviously we build out this model, we made changes to it, and if you remember at the very beginning, we also had these log files. Again, in a real world system, you're going to have gigabytes of these things, and let's say you're using coding agents to go and kind of make changes to some code. You want to make sure its understanding of what it does, like what the code does, is consistent with the production system. This will allow you to do that, because all of these effectively traces, what we can do is we can actually just write them out as IML code, and they're all kind of right here implemented. And um, you can see here what we're doing is we're just kind of creating this recursive function that takes the formal model and runs it against the traces. And here with Imandra's eval command, you can see that it actually is formally running the traces as the formal model itself. And so you can always check to make sure that, as you go from requirements from legacy source code, you create a model and it is consistent with, let's say, test cases that you have that are already existing or against the production data. Zara, do you have any questions at this moment? Yes, exactly. Yeah. So this is all Imandra X, and this eval command just basically executes let's say, the trace against the model. This verify thing that actually this bug that I thought was going to be fixed, but in fact it is not fixed. This actually runs the Imandra X verification command, and you can see here this counterexample is produced. You can, you know, say once this video is over and I'm going to go and through this code, what I'm going to do is, basically just try to understand why this verification goal, which is this kind of function, is false. Why this counterexample leads to that. But yeah, this is exactly that. So this is basically formal verification. It's running Imandra X in the background, and there is lots of things because for a lot of these functions, you'll deal with recursive definitions. So it's there's, let's say, a lot of magic under the hood that happens there. But I wanted to um, touch upon quickly what we kind of spoke about before, where our objective again when we're building out this, let's say, this executive um, let's call it a function that ties in all of our model components. It's the evaluator. Again, we take the state, the action, and we return what is the state. And for the objective of that we have is all of these scenarios that we constructed are consistent. So they're not, like, the predicates are not contradicting each other. Again, you can't have two, like one predicate says that, let's say, the counter is 0, and the other predicate says that, the account or the count is non-zero. So we want to be able to check for things like that. And also, we want to make sure there's no, for example, overlap between scenario S1 checks and scenario S2 checks. Because if that is true, then what we built is it's not a good model. And the other thing we want to do is we want to make sure that all of these, let's say, these 4 scenarios completely cover the state space. So all possible input pairs of the state and action. That's when we know that we're actually, nothing has been basically left or lost in translation. We have something that is complete. And then furthermore, we'll go in the next video, we'll show you how once we have SpecLogician, because this is difficult to do here, we'll start to actually say, okay, well, for, we have these 4 scenarios, they're all consistent. There's nothing, no other functionalities left. And we've looked at the logs and we see no logs that correspond to scenario 2. And so what is the problem? Is that something that is just not implemented anywhere? So it exists in requirements and it has been formally modeled this way, but it doesn't appear anywhere in the log files, etc. So you can see how we're going to start to pull in all of these different resources together. But before that, I wanted to show this kind of, want to talk about under specified models. So how do we know that all possible combinations of state and action are covered by these scenarios? Because again, for anything in real world, there's going to be virtually infinitely many of those guys. How do we know that? And we can actually start to use something called region decomposition. So this is a feature of Imandra where we can take all of these guys and let me go try to visualize it. And it starts to tell us, okay, it's a very generic feature and it's very powerful. I urge you all to go to imandrax.dev. There's a special section on this. There are lots of different ways you can use it. But what we're using it here is to symbolically describe to us regions of the state space that are not covered by this. So we have this nice Voronoi thing, and we have also these kinds of effectively regions described. And this is code that is kind of very raw output. The CLI that you'll see that we have for SpecLogician makes this in a kind of prints it out in a much better way. But what this is doing is this is telling us under what conditions that function returns true or false. And so we can use that here to identify symbolically what regions of the state space are not covered by these 4 basically scenario definitions. And for example, here you saw that a couple of these guys, a couple of those regions had false in them as the kind of invariant result. And it's easy for us to know this using formal verification that in fact, just because we have, there's a basically S and A, so the value of state and action that is not covered. So this is right here, is just a verification goal that says for any S and so the value of the state and the value of the action, they're always covered. So basically it says, it has to be one of the 4 scenarios. And we express this as a verification goal. And here it says, okay, actually for this combination, it is not covered. So what effectively, like if we were to run region decomposition and it gave us all regions where something was true, so there was no regions of the state space where the output was false in this case, then this would come back as proved. But since we do have these gaps, these kind of in the state space that are not covered by these 4, then we get a counterexample for this. Now, you might ask, okay, why do we need region decomposition if we just have this stuff? What actually region decomposition does in this case is it starts to provide to us a lot of very useful information about the conditions that are not specified here. And this is really key because, again, you want to, for real world systems, you're going to feed a lot of information there. And what Imandra via kind of SpecLogician will do is it'll say, hey, under these conditions, I don't know what to do. So these like regions of the state space are not specified. So you should look for information either in requirements, legacy code, everything else that will help you understand what this functionality should be. And this is really kind of, a big deal for going through these systems and formalizing them, because if all you have is, just go through this guy here, he says, okay, well, this is not covered. Okay, that's one, but I get this counterexample. What's special about it? Well, region decomposition will actually give you symbolic constraints that describe these different edge cases, not just concrete values. And that is something that's just so much more powerful for an LLM, where it says, hey, here's a symbolic definition of the feature you should look for and try to figure out what the system should do when those things are true. So, so it all kind of plays in nicely together for this. So yeah, the slides we'll put them up tomorrow. The this code as well. I'll go and fix this interesting thing that was supposed to be true, but in fact it is not. And the video next week will walk you through how you can use the kind of CLI utilities together with Claude Code. We'll use that probably to just teach Claude how to use this kind of framework, and then it goes off on its own and just pulls in this data, creates this formal model. At the same time, the framework itself will run through all of the various consistency checks and recommendations and generate recommendations, so forth. So, and that will allow you to, go into any kind of software projects armed with an AI coding agent and know that you're not just kind of, randomly guessing, or, you're leaving things up for hallucination or something might have been left out or something. You're really creating this logically consistent and rigorous framework for how to think about the what's called mathematical context of your software system. So we're at 50 minutes. I think this is a good place to stop here. Again, there's a lot of stuff that we've covered today. We'll post the stuff online, and next week we'll start to use Claude together with the kind of SpecLogician, which is the framework that does this to produce these things automatically, not manually. Awesome. I think we can call it a day. So, guys, thank you all very much for joining us, and until next time.